because of COVID-19. I'm very happy to see you in person. And I have three announcements. First one is, as you may know that toric topology, this subject was registered as AMS subject classification. Do you know that? That number is AMS mass debut 2020.
2020.
And subject classification number is 57 12. Right? So if you write a paper related to toric topology, please use it. And that's one announcement. Second announcement is Osaka City University and Osaka Prefecture University were unified last April. So now, so this is a first conference after the two universities were unified. And OCAM is originally the name of OCAM is, you know, Osaka City.
Advanced Mathematical.
No, Osaka City University Advanced Mathematical Institute. But since the two universities unified, I don't know who had this idea, but anyway, the OCAM is the abbreviation of Osaka City University Advanced Mathematical Institute. But since the two universities unified, now the name of new university is Osaka Metropolitan University. No. University. Name of university. Osaka Metropolitan University. So, but it doesn't fit OCAM. Yeah? but they created a new name for OCAM. Osaka Central Advanced Mathematical Institute. So the abbreviation is the same as OCAM. But anyway, that's the second announcement. And the third announcement is we take a group photo. Okay, and also tomorrow, twice. At the beginning of afternoon session. Okay. So afternoon session starts at 2 o'clock. Okay, so we take a photo at 2 o'clock.
Here.
Okay. So if you don't come, that picture and then photo shows you are absent. But anyway, and so let's start. But that talk is before 10
Yeah, but I have 10-6 or
10-6 already. Okay, so I'm now the Carol is here.
Okay, welcome to today's morning session. So I'm honored to introduce first speaker, Anton Ayzenberg from HSE. He's going to talk about equivalent formality of isospectral matrix manifolds.
Okay. Thank you, Shintaro. Yeah, and thank you, Professor Masuda and Shintaro, for inviting me here. That's okay, me here. I'm also very glad to see you all in person. That's really nice after all this COVID times. So yeah, I'm going to speak about equivariant formality of isospectral matrix manifolds, and actually this subject contains like two sub-subjects, something related to matrix spaces and something related to some general toric topology. So I will speak about this, but actually this is a joint, so my talk is based on several works with different people, with Mikia, with Grisha Solomadin, who are here, and also with Professor Bushtaber, with Vlad Cherepanov, and with my PhD student, Kostya Sorokin. So, okay, let me start with some basic construction. So I fixed some graph. So this is kind of different from what we have in toric topology. In toric topology, we usually we usually start with some polytopes or stuff like this. But here, my basic combinatorial object will be a graph, just a simple graph on n vertices with some edge set E gamma. And I want to consider matrices of the given shape determined by gamma. Essentially, what types of matrices I am considering? Okay, if you prefer a complex number, then you should consider Hermitian matrices, complex Hermitian matrices of size n. If you don't like complex numbers, then you can consider real symmetric matrices, and everything will work for real matrices as well. But this requires some discrete torus actions, some real torus actions instead of compact torus actions. And what I mean by matrix has gamma shape. This means that all elements of a matrix which correspond to non-edges of the graph should be zeros. So here are some examples. So for example, if you have this graph with edges 1, 2, 1, 3, and 1, 4, then I allow elements 1, 2, 1, 3, 1, 4, and symmetrically these elements. And I also always allow elements on the diagonal of a matrix. But all other places should be empty. So this is first example. So when you have, for example, this star graph, then you have what we call arrowhead matrix. So it has first row, first column, and diagonal. And you can guess that if you take full graphs, then you get all matrices with all entries. So this is just the space of all symmetric or Hermitian matrices. And for example, this sparse graph corresponds to 3 diagonal matrices. This is also easy to see. And also there was one interesting example that if you take cycle graph, then you get what we call periodic 3 diagonal matrix. So this is just like 3 diagonal matrix, but you also have, you may have some elements here in these corners, but all other elements are zeros. Okay, so here are some examples what we consider, but essentially this space, the space of all such matrices of the given form is not very interesting. It's just a flat space because I can put zeros like 0 somewhere, and instead of stars you just have some, well, any number, well, preserving this condition for the matrix to be Hermitian. So actually this space of such matrices is not very interesting, but it becomes much more interesting if we restrict eigenvalues. So I fix some collection of eigenvalues. Eigenvalues, so a collection of eigenvalues I call a spectrum, and a spectrum, so if your matrix is Hermitian or real symmetric, then the spectrum, of course, we all know that it should be real numbers. I assume that all these real numbers are pairwise distinct. So this is what I call simple spectrum. So I always work with simple spectra. I don't have repetitions in here. And what I basically do, I consider the space of all matrices of given shape, which also have given eigenvalues with the given spectrum. So I intersect the space of, well, this flat space of all gamma-shaped matrices and the space of all matrices which have spectrum lambda. And this is what I call M gamma lambda. So this is the basic object for me. And it should be noticed that okay, we prefer to work with manifolds, right? So it's good that if objects are smooth manifolds. And essentially we don't know, so this is a kind of open, in general it is open question, if you have some given graph gamma, how to describe all lambdas, all sets of lambdas, such that this intersection is a smooth manifold. So we do not know. We know in some particular examples, in very restricted class of examples, but in general, this is an open question. But what we know is that if you choose lambda generically enough, then this becomes a smooth submanifold, and this is basically by Sartre's lemma. So if you consider generic like input generic lambdas, then you get something smooth. So in the following, I'm always assuming that lambda is chosen generically. So I'm considering smooth manifolds, but I don't know precisely which lambda are generic. So I know that there is an open dense set of lambdas which give smooth manifolds, but I don't know precisely what is this set. This is also a question. I don't know. Yeah. So, but I consider like any lambda for which this is smooth. I don't know if they are diffeomorphic to each other or not, but actually what I will formulate works for any such generic lambda, for any such generic manifold. Okay, and some simple dimension count tells you that this manifold should have this dimension. This is twice the number of edges of graph gamma. Yeah, twice if you consider Hermitian matrices, and just number of edges if you consider real symmetric matrices. Okay, so here some basic observations that actually we have a unitary group which acts on Hermitian matrices by conjugation. Just very basic things. This is kind of, I would say, coadjoint. So this is a coadjoint action of UN on its tangent or cotangently the algebra, basically. And so we have this action on the space of all matrices, and this action preserves the spectrum, but it may not preserve. Sometimes it doesn't preserve the particular shape of a matrix. So this UN action is good to study like MN and M lambda itself, but not gamma-shaped matrices, because it can like break the shape of a matrix. However, if you consider the maximal torus in UN, the maximal torus of diagonal matrices, then of course it also preserves the spectrum, this conjugation by such matrices, and also it preserves preserves any shape. So okay, this kind of I have some matrix. So this is an arrowhead matrix given as an input, and here is a torus, and I can kind of act by a torus on a matrix. So you can see that this action just changes all non-diagonal elements, but if some element is 0, like here, then it is still 0, right, after the action. So this action preserves gamma shape, and this is why we have a torus action on the set of all gamma-shaped matrices with the given spectrum. So our manifold basically has some torus action, and so for us this is the very interesting class of examples. So we have examples of smooth manifolds which are acted by some kind of big torus. So it has dimension, and effective action is n-1 dimensional. So we are interested in toric topology of these manifolds, and we study these manifolds using toric topology. All right, so let me recall something very briefly, some general notions from toric topology. Actually, probably I will it will not take too much time. So if I have some torus action on a smooth manifold X, then of course you can consider the set of P fixed points. So in my talk, it is assumed to be non-empty and finite. So this is isolated fixed points, and so this is denoted by xt, and we also have some bunch of homological constructions related to torus sections. This is a Borel construction, which is kind of homotopical fiber of the action, homotopical quotient of the action on X. And we have the self-fibration from the Borel construction to the classifying space of a torus. And we can define equivariant cohomology as cohomology of Borel construction. And we have spectral sequence which relates ordinary cohomology of X and equivariant cohomology of X in some nice way. So it starts with the tensor product of ordinary cohomology and polynomial ring. So this is this cohomology of BT is just a polynomial ring, and it converges to equivariant cohomology of X. And in sense of these general definitions, there is the notion of equivariant formality. So equivariant formality of X means that this spectral sequence collapses at E2. So basically, you have a very good relation between ordinary cohomology and equivariant cohomology of X. So this is the definition. So this is also called equivariant cohomological equivariant formality in terms of Koreski, Kotrits, Macpherson. But yeah, I just call it equivariantly formal. So these are kind of good spaces from cohomological viewpoint. But actually, this is a kind of very complicated definition because it uses some abstract things like spectral sequences and so on and so forth. But there is an equivalent definition for those torus sections which I'm interested in. So whenever a torus section has isolated fixed points, then equivariant formality is the same as vanishing of odd degree cohomology. Well, basically, you should put some coefficients everywhere. So you should define equivariant formality over some ring R. And here also there should be R, some coefficients. But anyway, vanishing of odd degree cohomologies is something very, very cool and nice. Yeah, just a little comment that of course, if you are working with real matrices, with real symmetric matrices and some real spaces acted by a real torus, you do not expect such sort of statements. So in these spaces, we have cohomologies in degrees 1, 3, in odd degrees, but there is still some very nice equivalent definitions. So there is a notion of equivariant formality. You can just kind of look at the previous slide and also consider some Z2 equivariant cohomology in case of discrete torus section. But still, there is a notion of equivariant formality for a real torus, for discrete torus. And still, equivariant formality, whenever I'm telling about equivariant formality in the following, this works for real spaces with Z2 coefficients as well, but there is no such statement as this one. So this is for a complex case. And well, actually, okay, let me stay in the complex universe. So I'm considering spaces of Hermitian matrices of the given shape and some given lambdas which are generic enough. And I wonder for which graphs gamma such manifolds are equivariantly formal. So this is the problem that I'm going to solve. Yeah.
Possible to be torus manifold in gamma lambda.
Yeah. So yeah, torus manifold. Yeah. So yeah, there will be examples. I think. Okay, there are examples. Nice. But I need to. Okay, maybe now I need to. Okay, let's start with some basic example that when we have a full graph. So the full graph corresponds to full matrices, which may have entries everywhere. Yeah, of course, some of these stars may be zeros. That doesn't matter. But anyway, if you consider the space of all matrices, and if you fix a spectrum, then you can notice that this is actually a full flag manifold, full flag variety, because you have this UN unitary group action by conjugation on such matrices, and you know that it preserves a spectrum, and we also know from some basic first course linear algebra that any Hermitian matrix can be diagonalized. So essentially, this action of UN on this space is transitive, and you can notice that it has stabilizer the torus of diagonal matrices. So you can see that this m lambda is the quotient of UN by T. So it is a homogeneous space. And so this is a full flag variety. And full flag variety is known to, this complex full flag variety is known to be equivariantly formed, right? Because we don't have, well, for example, we have Breuer decomposition into even dimensional cells. So it doesn't have odd degree cohomology. So this is basically this is not just a manifold. This is a variety with some algebraic torus action, and you can use these fancy results like Galinitsky-Birula theory to notice that this is actually equivariantly formal. So this is the first basic example. So in this example, we have equivariantly formal space, and another example which is also well studied is the case of three diagonal matrices. And this is a toric manifold. So this is a quasi-toric manifold, I would say, because you can just use some dimension count. I mean, you have, okay, so this graph has, okay, for example, this graph has three edges. So dimension of this manifold should be 6. But the torus action is three-dimensional. Okay, you have four-dimensional action, but you forget about one-dimensional non-effective component diagonal. So you have manifold of dimension 6 with three-dimensional torus actions. So this is a torus manifold. So, but actually, this is not just a torus manifold. It is a quasi-toric manifold, and it follows from some old results of Tomei, 84. Carlos Tomei. So he proved, so at that time, there were no quasi-toric manifolds, right? So he didn't know all this stuff. And here, actually, he considered real matrices. So he considered the space of all real matrices of this given shape and fixed the spectrum. Well, first he proved that this is always smooth if spectrum is simple. So you don't need this genericity condition, so it is always smooth. And second, he proved that whenever you restrict your matrices even more, whenever you put positive entries here, real positive entries above diagonal. I can use this, okay. Whenever you make this additional restriction, then this becomes a manifold with corners diffeomorphic to permutohedron. But basically, you can notice that if you take positive entries here, then this is just the orbit space. So when you act on the whole space of such matrices by a torus, this means that you kind of rotate these entries, and you can always rotate them in order for them to become non-negative real numbers. So basically what Carlos Tomei proved is that the quotient, so the orbit space of such manifold is a permutohedron. And so this becomes a quasi-toric manifold over a permutohedron. And this was basically one of the motivating examples of Davis and Januszkiewicz in their seminal paper. Because, yeah, okay, they generalized toric varieties. Yeah. Sorry, yeah. So, oh, yeah, that's a mistake. Yeah, it should be, without. So this was a motivating example for Davis and Januszkiewicz because they kind of introduced generalization of toric varieties. But do we have any other interesting examples? And here is one of the examples. So this manifold of isospectral three diagonal matrices is a quasi-toric manifold, but it is not a toric variety. Essentially, this is this mi and lambda is is determined by characteristic function given by coloring, by proper coloring of permutahedron. So this is not a fan, This is this coloring. Okay, so this was example of 3 diagonal matrices, and you can kind of interpolate between all matrices and 3 diagonal matrices in a way that is familiar to many of you who study Hessenberg varieties. That of course you can take, well, instead of 3 diagonal or full matrices, you can take like staircase matrices, Hessenberg matrices. So this is Hessenberg matrix. So it corresponds, yeah, of course it corresponds to some graph, right? So this shape, staircase shape, is also kind of good shape, and actually they appeared in the works, some older works of De Mari, for example, who introduced Hessenberg varieties, and in particular, real case of this construction was just determined. It was introduced in the paper of De Mari on real Hessenberg varieties. This is not actually a real Hessenberg varieties, but what they called real Hessenberg varieties. This guy, I don't know. I think this is some mistake, but yeah. But anyway, we also considered with Victor Buchstaber, we considered space of Hermitian matrices of such form. We also proved that it is a smooth manifold when spectrum is simple. And we also noticed that it is equivariantly formal. So this general class gives equivariantly formal spaces. And this is basically proved using Morse theory. So we just noticed that there is some function with Morse function with stationary points of even indices. So this manifold has decomposition into even dimensional cells. So all these examples are equivariantly formal: 3 diagonal matrices, full matrices, and the staircase matrices. But actually there are more interesting examples. So there is an example of arrowhead matrices. So for example, if you take this graph, you get this matrix, which is not staircase in any sense. And actually, we knew about these matrices from Januszkiewicz. Like I knew about such matrices from Januszkiewicz in 2016. So he told me that they have some work with Svetoslav Gau about such matrices. And he told me that yeah, we have some result, but I don't know if they published it or not. So I'm checking it from time to time. But essentially, what he told me is this one. So in this case, yeah, okay, you can notice that in this case you also have torus manifold, because dimension of this manifold is 6, and torus action is 3-dimensional. So basically, you expect that the orbit space should be a manifold with corners. But they noticed that this is manifold. This is not a polytope. This is a solid torus with its boundaries subdivided into hexagons. So this is still some manifold with corners, manifold with faces, and it is kind of simple because in each vertex you have three facets meeting. But basically, it is not a polytope. So in this case, you can use results of Mikia and Taras, which gives a characterization of equivariantly formal torus manifolds. And since this guy is not a polytope, and it doesn't even look like a polytope, this manifold is not equivariantly formal. So this is a kind of counterexample. Okay, so we have this non-formal example, and another thing that I studied is this manifold of matrices corresponding to this cycle graph. So these are periodic 3-diagonal matrices that I told you, and for me it was interesting. So I was motivated to study this because it is an example of complexity 1 action in general position. This is what I told yesterday a little bit about. So this is a complexity 1 action in general position, and so in particular you expect you expect that the orbit space in this case should be a topological manifold. This is some connection to my yesterday talk. But well, essentially, what I proved here is that this this manifold is not equivariantly formal when n is at least 4. This is a very natural thing because when n is 3, then you get just full graph. So full graph corresponds to full matrices, and this is just a flag variety. So you do not expect it to be non-formal. So some strange things start to happen when n is at least 4. So you have some zeros right here. And this is not equivariantly formal. And this can be seen like in two ways. So maybe like the simplest way to see this is that I computed a fundamental group of this manifold. I should notice that actually this guy may be singular. So sometimes for some simple spectra, this becomes a singular space. So it may have some degenerations. And I also described the topology of this guy, even if it is singular. But if we restrict to the case when it is smooth, then its fundamental group is like this. So this is basically this is an abelian group z to n minus 3. So you see that if n is at least 4, then this is non-trivial, and its abelianization is also non-trivial. So this manifold has first homology, non-trivial. Even first homology makes it non-formal. But maybe a bit more interesting way to prove this non-formality is another. So this is basically this was same paper, but we had result with Mikia that whenever the action of complexity 1 in general position is equivariantly formal, then the orbit space should be a homologous sphere. Like I told you yesterday, that for Grassmann manifold and for flags F3, you have spheres by theorem of Buchstaber and Terzic. So we kind of generalized this for complexity 1 actions in general position. So the orbit space should be a homologous sphere, but in this case, for such matrices, the orbit space. So I proved that the orbit space is the product of a sphere, so 4-dimensional sphere times some toric components. So when n is 4, oh sorry, that's there should be, I think, tn minus 3. Yeah, right. When n is at least 4, so this becomes non-trivial, right? So this is not a homologous sphere. It is more complicated space, and it is also interesting. So I mentioned here that what is the origin of this torus? So you can see that I took a quotient by a torus. So this torus orbits they disappeared, right? So each orbit becomes a point. So what is this torus? And actually, this torus comes from mathematical physics. So basically, these matrices of this shape were studied in mathematical physics in relation to discrete Schrödinger operator and also some so-called periodic Toda flow. So actually, there is some sort of dynamical system on this manifold, not only torus action, but also some dynamical system, which is kind of quasi-periodic. So it is integrable, and closures of its trajectories become tori. So they are Liouville-Arnold tori. So actually, this torus comes from mathematical physics. This is a Liouville-Arnold torus, and this kind of interesting, I think, that we have this physical explanation of non-formality in some sense. So these are examples. So we have two classes. We have like staircase matrices, which give equivariantly formal spaces, and we have these cycles which are non-formal, and we have this star graph, which is also non-formal. So okay, let me go further. So let me describe which which graph correspond to staircase. Yeah.
So it seems that m lambda, m gamma lambda is not algebraic, right?
Not algebraic, yeah.
Is there any criterion for the graph? So see m gamma lambda is algebraic?
I believe that for any graph, it is not algebraic variety, but I cannot prove it. So it is not complex algebraic in the sense that it is not given by any complex algebraic relations. So it is not algebraic variety in some natural sense, but to prove that it is not diffeomorphic to any algebraic variety, this may be complicated. I don't know the answer, so I think this is open. Yeah, that's a good question. Yeah, thank you.
Gamma is narrow for the complex graph.
It is not complex, even in all these examples when they are equivariantly formal. I don't believe they are algebraic. I think this can be proved using some characteristic classes or characteristic numbers, but I don't know. I think that nobody knows. Yeah, that's maybe good question. Yeah, thank you.
The tangent bundle of your M gamma is
Stably trivial. Yeah, so my all these manifolds that I'm considering are stably trivial. Stably trivial. So yeah, tangent bundles become trivial if you add some trivial summands. Yeah, I think that maybe for this reason, maybe you can prove it that they are not algebraic, but I don't know such statement that. Yeah, I mean that there may be some algebraic varieties with trivial bundles, tangent bundle. So I don't know. This is just my belief. Okay, so now very basic combinatorics, that graphs corresponding to staircase matrices are so-called indifference graphs. So indifference graph is basically a graph given by you have some line, real line, and you have some intervals of unit lengths. You put some intervals on a line, and then you take intersection graph of these intervals. So if some intervals intersect, then I draw an edge between corresponding vertices. So for example, this 1, 2 intersect, we have this edge 1, 2, 1, 3 intersect, we have this edge, and so on. So this graph corresponds to this configuration of unit intervals. And there are also several equivalent names for these graphs, like they are also called unit interval graphs or proper interval graphs. Yeah, well, you can understand why they're called unit intervals, because, well, these are unit intervals, right? Proper interval is kind of it is also given by some collection of intervals on a line, but with some weaker restriction, but still this corresponds to the same types of graphs. And it is known that such graphs are exactly those graphs corresponding Hessenberg matrices. So these are graphs representing matrices of staircase of this shape. All right, so so this is kind of the answer: which graphs correspond to staircase shapes. And you may guess that some graphs are not unit interval graphs. For example, this star with 3 rays. You can easily see that you cannot place 4 intervals on a line to get this graph as an intersection graph. So it is more complicated. Okay, but here is one warning that it is not very difficult, but sometimes you have matrices which are staircase, but they do not look like staircase. Like, for example, if you take this matrix, so this is arrowhead matrix of size n, of size 3. Actually, I want to say that this is actually a staircase matrix because, well, this matrix corresponds to this graph 1, 2, 3. But actually, this graph is an indifference graph, right? So you can realize this graph as a sequence of as a sequence of intervals, as coming from a sequence of intervals on line. But in order to do this, you need to change labels. So instead, you need to change 1 and 2. This corresponds on a matrix. This corresponds that you relabel some rows and some columns. Like you change first and second row and first and second column, and then you get this matrix, which is of course staircase. It is 3-diagonal matrix. So sometimes, and of course the spaces, isospectral spaces of such matrices are the same. They are homeomorphic, diffeomorphic, and stuff like this. So equivariantly diffeomorphic. So it is very easy to see by permuting some labels. So for me, this shape of matrix is also good. Also, it is not staircase, strictly speaking, right? Okay, so here is to our result. So first some preparation. Notice that this torus section on my manifold for any graph gamma has n factorial many fixed points. So they correspond to, if you remember that I showed you how torus acts on the matrix, this torus doesn't change diagonal elements. So essentially, when you act by a torus, then fixed points should be diagonal matrices. But since you are working with isospectral matrices, these diagonal matrices should have spectrum, the given spectrum lambda. And these are given by all permutations of lambda. So they are n factorial many fixed points. It is very easy to see that they are isolated, and then their number is this guy. And of course, we have a statement when you have some compact torus action on a manifold, then Euler characteristic of a manifold equals Euler characteristic of the fixed point set. But for the fixed point set, Euler characteristic is just the number of these points, so this is n factorial. So we have this result that Euler characteristic of our manifold is always n factorial. This comes from a very basic toric topology. But there is some conclusion from this. It is very simple, but I was very happy when I found it because it is kind of very simple interpretation of what we have in toric topology. That essentially this tells you that total Betti number of this manifold is at least n factorial. So it cannot be less than n factorial. It is kind of from topological point of view, this manifold is kind of very complicated. It has many Betti numbers, n factorial Betti numbers, at least n factorial Betti numbers. And here is our result. So actually we prove that the only equivariantly formal manifolds of this of gamma shape are those corresponding to indifference graphs. So basically, the list of staircase matrices, staircase matrix manifolds is an exhaustive list of equivariantly formal examples. So no other graph gives equivariantly formal space. And this also gives another equivalent condition that so gamma is indifference if and only if the total Betti number of this manifold is exactly n factorial. Well, this follows easily from these two observations here, because equivariant formality is about beta odd being 0, right? So if you have beta odd 0, then total Betti number of the manifold is equal to Euler characteristic. This is just n factorial. And if it is not equivariantly formal, then you have some odd Betti numbers. So this guy becomes strictly larger than n factorial. So in some sense, there is an alternative. This manifold can have Betti number n factorial or bigger than n factorial. And the first case corresponds to indifference graphs, and the second case corresponds to non-indifference graphs. Okay, so let me continue. So this was our main theorem, but essentially I have before I give you a hint of a proof how to do this, there is some corollary about some sort of applied mathematics. Essentially, this is a corollary about some algorithms on matrices. But there are no algorithms on this slide. But okay, what is the corollary? If gamma is not in difference graph, then as I told you, this total Betti number should be strictly bigger than n factorial. But this means that if you take any Morse-Smale flow on m gamma lambda, so for example, any Morse function on this manifold, then it has more than n factorial stationary points. So this is just some consequence of Morse inequalities, right? So if the total Betti number is more than n factorial, then the number of stationary points should be more than n factorial. And this gives some intuition why it is kind of expected, why is the whole theorem is some sort of trivial. So actually we have such well-known thing as QR algorithm. So it is very useful thing in applied linear algebra, because whenever you want to diagonalize your matrix to find eigenvalues, I think that the best thing you can do is to use QR algorithm. This is kind of asymptotical algorithm. It doesn't give you precise answer, but it works like this. So you have some matrix. Let me write some entries here. So you start with a given matrix. I assume that it is Hermitian or real symmetric. I have a matrix, and then I do infinitely many steps. Well, in practice, not infinitely many, just some finite number. But what is the step? The step is that I decompose a matrix into the product of Q and R. I don't remember Q. Q is orthogonal and R is upper triangular. If you speak about real matrices, for example. So I decompose this matrix into Q times R, and then I interchange and take the matrix R times Q. And this is one step. So when I perform this step, somehow my matrix changes, and it changes in a way that after some number of steps, the matrix becomes after infinitely many steps, the matrix becomes diagonal matrix. And this is the answer. So this is these are eigenvalues of the original matrix. This is how QR algorithm works. And essentially, this is based on the observation that this QR algorithm preserves spectrum and symmetricity, or Hermitian property if you are speaking about complex matrices. And this QR algorithm has always tends, well, not always, but in general position, it tends to some limit point. And these limit points are diagonal matrices with some diagonal matrices of the given spectrum. So actually there are n factorial many limit points, and actually you can see that this QR algorithm becomes a more Smale system on the manifold of isospectral matrices. So every trajectory tends to somewhere, and these limit points are kind of hyperbolic type or something like that. So essentially, this is a discrete time dynamical system, which are also called cascades. Cascade is a dynamical system with discrete time, but there is still a notion of Morse-Smale flows, and there are still Morse inequalities for such systems. This was proved by Smale. So essentially, you can consider your QR algorithm as some sort of gradient flow, as some sort of Morse flow on a manifold. So this acts on a manifold of all matrices with the given spectrum, but you can notice that if you if you start with some matrix of staircase shape, then after making steps, this still preserves this shape. So if we have zeros somewhere, then there are still zeros at those positions. So essentially, you can notice that this is also this QR algorithm is also a dynamical system on the matrices, on the staircase matrices. Okay, maybe if you don't like dynamical systems with discrete time, there is a continuous version of this QR algorithm called Todaflow. It is just an ordinary continuous system with the same properties. So it preserves some gamma shape and all this stuff. Okay, so basically, well, returning to this stuff, our theorem tells that okay, we certainly have this dynamical system for staircase matrices, but this dynamical system has n factorial limit points. So this proves that the sum of Betti numbers cannot be more than n factorial. Again, by Morse inequalities. So in staircase shape, this just proves equivariant formality. But in all other shapes, for non-indifference graphs, our theorem tells you that there is no algorithm which asymptotically diagonalizes well, non-staircase matrix, because any such algorithm, if you want to diagonalize, you need some diagonal matrix with a spectrum on diagonal, but there are n factorial many such points. And we prove that you cannot have n factorial limit points. You always have bigger number of limit points. So this just shows that, okay, staircase matrices can be diagonalized very quickly by some asymptotic algorithm, but in other shapes, there is no such algorithm. Yeah, of course, QR algorithm does not preserve non-staircase shape, but you don't have any other algorithm like this. So this is the idea. And now, so how do we prove our theorem? So the essential part of our theorem is about the implication that if gamma is not in difference graph, then this manifold is not formal. And here is a lemma. That's actually this lemma is contained well in more general formulation. It is contained in the work of Mikiya Masuda and Taraspanov in Osaka Journal of Mathematics. That essentially, if this manifold is formal, and if you have some induced subgraph of gamma, then the manifold corresponding to this induced subgraph is also formal. So induced subgraph means that what is written on this example. So if you have some graph and you take some collection of its vertices, you should include in your subgraph, in your induced subgraph, all edges of the original graph gamma connecting these vertices. So this is an example of induced subgraph, and this is not induced because here is some edge which you should include for this graph to be induced. So of course, every graph can be a subgraph of a full graph, but in a full graph, induced subgraphs are only full subgraphs. So that's an important point. And from this lemma, it follows that when we prove non-formality, okay, there are many non-indifference graphs, right? But we can, in some sense, we can restrict to minimal non-indifference graphs because we have this lemma. So we don't need to consider all non-indifference graphs, just some small graphs. And essentially, there is a very nice theorem of Roberts, some old theorem in graph theory, which tells that the criterion for a graph to be non-indifference. So a graph is non-indifference if it contains one of the following induced subgraphs. So this guy, they call it claw. Holes are cycles of length at least 4. And this strange sink and this strange sink. So this is called the net, and this is called 3 sun. I just call it sun because I don't have any other suns here. So these are restricted subgraphs. Of course, if you have induced subgraphs like this, then your graph is not indifference. This is a very simple exercise. But the theorem is that the opposite also holds, that if graph is not indifference, that it has one of these induced subgraphs. So we only need to prove non-formality for this collection of guys, right? And this is very nice because this kind of finite, well, not finite, there is an infinite series here, but still this is kind of finite list of what we can do, right? So we already seen these two examples before. So I told you that this is not formal. This is what Januszkiewicz did, and we also like checked it with Buchstaber. And these are also non-formal, just when k is at least 4. So I also checked non-formality for this infinite series of examples. And it only remains to think about these two strange graphs, why the corresponding spaces are not formal. So actually we used some general approach here. So there are a couple more definitions from toric topology. So assume that you have some action of torus on a manifold, and assume that you have some connected subgroup in this torus. Connected, yeah, closed, I guess. Well some subtorus inside T. And you can take the set of fixed points, H fixed points on the manifold X. This is just some submanifold, maybe disconnected. And I call the connected components of these submanifolds invariant submanifold. And I call an invariant submanifold a phase submanifold if it contains a T fixed point, at least one. So I introduce a notion of phase submanifold in X. So this is defined by some torus section. And we can introduce some ranks attached to this space submanifold. So the rank is the dimension of a generic toric orbit on this phase submanifold. And we notice that these phase submanifolds are partially ordered. So they give some combinatorial structure associated with the torus section in general. I mean that you always work with, many of you work with polytopes, and polytopes is some kind of combinatorial structure, but this is kind of a bit more general combinatorial structure. We have some partially ordered set of phase submanifolds. And for example, like minimal elements of this partially ordered set are just fixed points of the action, and the greatest element is the manifold X itself. So I consider this partially ordered set. This is some finite partially ordered set of phase submanifolds. This is some combinatorial object associated to a torus section. And then I consider all phase submanifolds of ranks at most some given number. This gives some what is called equivariant R skeleton. So if you take one skeleton, this is what is called GKM graph, basically. And this is kind of generalization. So instead of GKM graph, you consider higher dimensional structure. And actually this, I still require something from the action which resembles GKM things. So I require from the action that it's any phase submanifold of rank 1, so consisting of one-dimensional orbits, is actually a two-sphere. This is what is required in GKM theory, but in GKM theory, they also require some equivariant formality. But here, I don't know if when this is equivariantly formal or not, so I'm going just to prove it. But still, this condition about spheres, about two spheres, is satisfied for my manifold of matrices. And here is our result from the joint work with Mikia and Grisha. We proved some acyclicity condition of this skeleton if the action is equivariantly formal. So assume that we have some equivariantly formal action on a manifold X, And so there are some technical conditions here. This is I just wrote them for simplicity for this to be correct. We have some a bit more general theorem, but okay, let me restrict to this case. So suppose that dimension of a torus is at least 4, and suppose that I have ranks also at least 4. So this is the rank of equivariant skeleton is at least 4. Then this equivariant skeleton as a partially ordered set is acyclic. It is 3 acyclic. So it doesn't have cohomology in degrees 1, 2, 3. Okay, and 0 if you are speaking about reduced homology. So essentially, this partially ordered set, if you take its geometrical realization, it should be acyclic. This is a consequence of equivariant formality. And we can use this to study these spaces, these manifolds of such matrices. So just for fun, I have drawn these matrices corresponding to this graph and to this graph. So they look like this, very irregular, something very strange. I don't know how to treat these matrices. It's kind of seems complicated. So for example, this first manifold of these matrices has real dimension 12, and it is acted by a 5-dimensional torus. So the action has complexity 1, but it is not in general position and stuff like this. And this manifold has dimension 18. And of course, we cannot compute what degree cohomology of these manifolds by hand, because they are kind of enormous. But we can describe the partially ordered set of phase submanifolds in this case. And this is what we did. We described, in general, in a joint work with Victor Buchstaber, we described this partially ordered set of phase submanifolds for these matrix manifolds. And then if these spaces are equivariantly formal, then our results should imply that these partially ordered sets are 3 acyclic, as I told you. But this is something that we can check on computer, right? So these are finite partially ordered sets. This one and this one are partially ordered sets that you can type into a computer and check their homology of degrees 1, 2, and 3. And this was what my work with my student and faculty of computer science, who did some technical work of running all this stuff on computer. So actually, we just computed homology of these partially ordered sets. And it happens that it was kind of complicated thing, because we computed first homology, it was 0. We computed second homology, it was also 0. And then we tried to compute third homology, but it took several days at some very powerful computer. But still, so Kostya managed to, so he just guessed that it will be easier with Z2 coefficient. So finally he computed this, and he found that these third Betti numbers are non-zero. They are 5. I don't know why 5 in both cases. Yeah, but we checked this should be correct. So this proves that these manifolds are not equivariantly formal, and this this proves the whole statement. Yeah, I'm sorry that I yeah.
So I have a question. Are there any typical properties when your spectrum are changed? I think in your mention, there's no effect.
Yeah, right. Yeah, because this partially ordered set of phase submanifolds is the same. So this partially ordered set of phase submanifolds, this main combinatorial object associated to torus actions, is the same. Even if manifolds are not diffeomorphic, this combinatorial structure remains the same. This is why we have this statement for any spectrum, because the spectrum does not affect this combinatorial structure. Yeah, but we don't know if they are diffeomorphic or not. Yeah, that's Yeah, probably they are diffeomorphic, but yeah, we don't know counterexamples. So we have counterexamples that this space can be singular. But even in this case, for the cycle matrices, even if it is not when it is non-singular, then all choices of generic spectrum gives diffeomorphic manifolds. So I don't know counterexamples, but maybe there are.
Any other questions or plans?
Yeah.
Any two base submanifold always transverse.
Well, yeah, they are. It depends on in which sense transverse. Which sense do you mean transversal?
In the big manifold.
Yeah, they are transversal, right? But you can see this locally if you look at fixed points. At any fixed point, then you have for each such phase submanifold, you can describe the corresponding tangent space, and they are well, they form some partially ordered set. So it depends on which dimensions you consider. Sometimes they lie in one another. Not always. Okay, not always transverse. They just give you some sort of well, this looks like, so just imagine some coordinate space arrangements, for example. So okay, if you have coordinate space arrangement, so is it transverse or not? Because yeah, sometimes intersections lie in some bigger space. So well, maybe in some sense they are transverse, but yeah, okay, maybe we can discuss it.
Questions?
Can you compute the equivariant cohomology ring or groups and check freeness condition?
Yeah, right. So actually, yeah. Thank you for asking. So there is actually, okay. So when we computed all this stuff, I had some doubts because it relates on some complicated computations. There can be some mistakes. So actually, I had some alternative proof of non-formality for these two spaces. Based on GKM theory. So I just had observations like, okay, if the spaces are equivariantly formal, then you can use GKM theory to describe, for example, equivariant cohomology. And I tried to compute several like second, fourth, sixth, and eighth equivariant cohomology using GKM theorem, by GKM theorem. And there is also some sort of contradiction to Poincaré duality, which can be extracted from GKM theory. So actually, yeah, there is another way to prove this using GKM theorem. So if it applies, then you get to some contradiction by computing. But it also requires some complicated computations, because there are some huge matrices of like size million times million, something like this. So you need to compute some ranks of matrices. Yeah. So we tried to compute something, but only in low degrees, because it becomes in higher degrees. It's complicated.
Excuse me, can I ask you a question?
Yeah.
Hi, Anton. So I wonder whether there are examples of torus manifolds among these manifolds.
Yeah. This is very simple answer. These correspond to trees. If graph is a tree, then
okay.
Yeah, basically, yeah. There is a there is a formula that complexity of this section equals first Betti number of a graph. So if your graph is contractible, then this complexity is 0.
Okay. Thank you.
Yeah.
Do you have any description of the orbit space?
Orbit spaces.
Yeah, torus manifold.
But no, we tried to do this, but we only have description in in the case of path graph, this is a permutahedron, and in the case of star graph, not just with 3, but with any number, we have a description of homotopy type of the orbit space. Well, maybe not the orbit space itself. And so, for example, when you have four rays in a star, then the orbit space becomes a wedge of 7 circles. Sounds, yeah, and you can compute some characteristics in higher degrees, but it is kind of very strange thing. So this homotopy type is, you can imagine permutahedron, and you take all faces of permutahedron, which are cubes, combinatorial cubes. And this gives you some cell complex. And its homotopy type is this homotopy type of orbit space. This is what we proved with Victor Buchstaber. But these are the only cases that we know for torus manifolds.
Yeah, one more question. There is an algorithm to construct the basis of the equivariant homology. I mean, the equivariant tone classes. If you have a flow on the GChem graph, some condition, the graph satisfies this condition, then you can construct basis easily by looking at emanating.
Right.
The emanating.
Like Morse theory for GCM graphs. Yeah.
Does this example satisfy this flow condition? With a flow without loops, correct flow without loops.
I think that any GK, I think that you can draw some sort of GKM graph here. I don't remember this condition precisely, but I guess that if you like place your graph somehow in the ambience in some Euclidean space,
you need to take into account the labels. So some GKM graphs that do not.
I'm not sure. Yeah, I thought that it is kind of some general theory like okay, there are multifans. So for example, in the multifan, you can have some intersections. I guess that's for any graph you can somehow place it into Euclidean space so that edges correspond to labels. So their directions correspond to labels. And I think that you can realize these graphs, these kind of GKM graphs of these manifolds. They can be realized in Euclidean space, and you can compute these indexes like in Morse theory, but they do not correspond to actual Betti numbers. That's a problem. Yeah, because they live only in even degrees. So these are kind of artificial things. They exist in big generality, but they don't know anything about topology. Yeah.
So ignore, let's stop speak again. So we will start at 11:30. Yeah. What is the time? Okay, 11:30.